Gravitational wave is a big idea in modern physics, which was first proposed by Albert Einstein just as he developed his general relativity. But in Einstein's opinion, it would appear human could never detect such a wave if there is any. However, a couple of years ago, just before the COVID pandemic began, an American group claimed that they had observed for the first time the gravitational wave from distant black holes. As a result, perhaps you know that Nobel Prize in physics were offered to some individuals behind this observation. Today, I will discuss this issue from quite a different perspective in order to provide you a complete picture about gravitational wave. Welcome to Yong Tuition. This is a unique channel to explore and share the knowledge about basic issues in physics and beyond. Please subscribe and also please inform your colleagues, classmates, neighbors to subscribe so that I can create more interesting videos. Let's go to the black ball. This is experimental result you can find in relation to this observation. And these two diagrams refer to the observation from the two locations. And the equipment they use is called the LIGO. LIGO for light interference gravitational observation. Obviously, this team has the two sets of the same similar equipment. From this diagram, you can see some oscillation appears above the noise, and eventually, during the course, the frequency increase and eventually disappears suddenly. So this phenomena was interpreted as the final moment when a binary black hole or neutron stars merged violently. Okay, so actually, there actually is two pieces of information. One is time-dependent or time series signal, as you can see this oscillation. But I must point it out that the signal-to-noise ratio was very poor, is less than 5. You see, so you can see that most of them, apart from this oscillation, they also got noise, a lot of noises. Another piece of information is the vertical. Can you see this banana-like profile? Actually, they call this signal as a banana signal. So you can see these the upper part of this display represents the Fourier transform of this oscillation. From this increment in the colored the banana, you can see that the frequency actually increase before this signal or burst disappear suddenly. So short, it's just a fraction of a second. So that was my first concern, is that how could that process just took a fraction of a second? Two black holes, huge size. How could that just like behave like two ping pong ball? Indeed, they just use a ping pong ball to display, to modeling this observed result. So this is mostly cited modeling of this observation. From here, you can see these two balls represent two heavy objects, which could be either a black hole or the neutron star. So as for some reason that when this the distance decrease, and then the angular momentum will decrease. So therefore, the spin evolution speed will increase, or angular momentum will increase. And that's why they use this phenomena to explain that the frequency gradually increase. And finally, the two black hole or black neutron star became one. So the merge just occur in the fraction of a second. See, in the fraction of a second. And that is actually this diagram. The lower diagram shows that how velocity. So this velocity change eventually reached to 0.6, nearly 0.6 c. So that is 60% of the speed of light. And while the distance decrease. But but this kind of description seems too simple and too simple to be believed. Why? Because we don't have to, oh, by the way, they claim that this prediction was made by using sophisticated theory, namely the field equation of the Einstein. So this is a field equation Einstein used to describe the general relativity. Okay, very, very abstract, because this is just notation. If you really want to use a particular coordinate and to consider the distribution, symmetry of the gravitational interaction, then you will notice that you take 100 pages to derive what you want to obtain. Yet, this team claims that they did use Einstein's relativity, but without use Einstein general relativity, that would be the talk later on. I can simply use this formula, this very simple formula, to generate a similar profile by using a free online software provided by Academo. I recommend Academo. Is a very good website. I have done many research using this website to visualize my experimental result, such as my study on climate change. Anyway, so that is just my first response to this simplified model. Namely, we don't have to invoke Einstein's general relativity in order to get this simulation. Well, by the way, they also, apart from this first observation, in the subsequent months or less than 2 years, they claim that they have observed more than a dozen of these similar events. So this is a connection of this observation by the same equipment and by the same team. So from this, if you zoom in into this diagram, you can see that the orange color represents the computer simulation, presumably based on Einstein's general relativity. And the green one represents the actually detected signal. In this case, the fitting is reasonably good. But if you just go to next one, you can see this modeling, this fitting is terrible. You can see in real case that there's no oscillation detected. Yet the theory predicts they must go through this oscillation in order to achieve this final moment. Okay, note of discrepancies. Of course, there are other issues, more fundamental than this just fitting. They have never explained properly how do they use their computer programming and statistics to manipulate their observed result. That is another issue I'm going to discuss today. So you can see the fit is not terribly good. It's apart from first one. So there are also a lot of discrepancy. Can you see here? There's discrepancy between the model and observation. But my point, apart from this simplification in their modeling, is that one doesn't have to invoke sophisticated and abstract, for many people, general relativity to explain these phenomena. Actually, so far, I have done several simple experiments in order to mimic this experimental result. So this is one of them. So this is one of them. This is oscillation I generated by using a pendulum. And this is the frequency. This is a frequency spectrum. This is a Fourier transform of this time series. Can you see the vertical line represents the frequency? So I can also obtain this banana profile, similar to the observed gravitational wave by LIGO group. Okay. Oh, before I go further, can we just demonstrate my experiment? I think I have got a few videos here. So can we play some of my experiment? So I did several experiments. Of course, the first one, perhaps someone have noticed in the previous video, is very short, very boring, just 10 seconds. I filmed that the vibration of the light bulb, which appears that the frequency is doubled toward the end of this toward this vibration. But here are another 3 experiments I have done subsequently. First, I use the ping pong ball to the experiment. So I just use this ping pong ball, and this is jump. Can you see? This is fall. But in the meantime, I did something slightly different. Yeah. So this is my ping pong ball experiment. Can you try again? Of course, in the meantime, I recorded this video as well as the sound. I use the sound waveform file to do my analysis, as you can see from here. Oh, 2 more experiments. Another one. So that is the equipment I use to generate this gravitational wave signal. The third experiment I just mentioned is this one. Is this, one moment, where are we? So this is a pendulum experiment. Can you see that the frequency increase as the length decrease? Let's just return to our sharing screen with sound. Yeah. So this is my last experiment using the pendulum to detect this oscillation, and that would be the frequency distribution after Fourier transform, which happened to be not exactly, very close to this experimental and theoretical profile reported. Based on that, some people, 2 or 3, got their Nobel Prize in physics. Okay. Of course, this is by no means to put down their effort over the past decades, or even more. You see, Einstein proposed this idea in 1920s or something like that. Okay, there's more experimental analysis. So these result, can you see this banana-like the frequency increase is obtained by using my a short fruit experiment. So that is how I detect the signal. There's more. So this is actually my ping pong experiment. So this is a ping pong experiment. From here, you can see that the frequency increase toward the end. This is actually the result, my first result. you can watch my the short video previously. That is my first time I noticed that even for the object, vibration and frequency will change, okay, toward the end. So that is where I started to consider this issue seriously. I heard of this report before, but this is probably this is in-depth investigation of this claim that gravitational wave has been observed. Now let's go to some theoretical, more serious concern. As far as the experimental design is concerned, nothing new compared with what Michelson and Morner did over a century ago when these two physicists were trying to verify whether there is an ether in space. Of course, their result is negative. Based on this result, and Einstein proposed developed his relativity, starting from special relativity in 1905 and to the general relativity in 1919. So why did these people call this experiment as LIGO or LIGO? I don't know. They should tell people that there's nothing new in the principle of this detector. Okay, compare with this is a centuries old equivalent by these two great physicists. Okay, they didn't mention it. That is the first, I think, is something inappropriate. Okay, instead of use LIGO, one can still call it a Michelson experiment method, right? It's interference of the beam. The only difference is the change in the light source from ordinary light source, monotone source, to a more accurate laser beam. So that is all. So the only difference between these two designs experimentally is that the arm is different. Okay, the arm is extended from 1 meter to up to 400 meters, as they described. Hopefully, they argued that when the gravitational wave eventually arrived at Earth, and these two arms, or one of them, or both of them, were experiencing this is a curved reaction, curved force. It's like the stress, like trace. You went to the material science, you know what is trace, you know what is the Yong modulus of the material. Yes, for the steel, that constant is huge, right? So in other words, the very small force can hardly make the change in length of the metal. Okay, but this still because in order to explain, in order to make their argument consistent, they have to assume that the detected signal is due to the bend or this stretch of these two arms or one of them, so that they can generate the tiny difference in phase of these two reflected laser beam. Okay, but is that reliable? Is this claim reliable? Well, we have to go to some detail, quantitative. You see, and but before we go, I have to make my argument that because this equipment is on the Earth, even there is a propagation of wave from distance in space-time arrived at Earth, the whole Earth will just simply slightly change, move slightly, be disturbed by this gravitational wave. Of course, the amplitude or the out of the stress will be dependent on the strength, critically dependent on the strength of the arriving gravitational wave. Okay, so it is from this picture, it's unlikely you will expect that some equipment on this boat will be affected, other than the whole boat is actually affected. Okay, when the wave, the tsunami arrived, is that you wouldn't just go back to see what happened to your pain. You just measure your pain if the pain is actually changing length, right? So you actually worry about most is that what have happened to this whole carrier, in this case, is our planet in the space, not space-time, but in space. So this is some more detailed description argument. So in general, if you apply the force from different directions, you would expect that the volume, the shape, will be distorted depending on two factors. One is the strength of the external force. Another is the Yong modulus. Obviously, if for the plastic and there's a much difference, apparent difference between the modulus between the plastic and the steel. You see. If we assume that these arms are made by steel, let's do some calculation. Okay. And yes, this experiment is indeed remarkable. Okay. Remarkable in what way? Okay. So that is our central concern of this video. Let's go to some quantitative. Okay, if we assume that indeed the two binary black hole merge, okay, and whose last moment was accidentally caught by this research group of their, once they turn on their newly designed, they build a toy, they catch this moment, okay, which is as short of fraction of a second. So if we just assume that is the hypothesis is true, that the gravitational wave will go all directions, right, from that source, which according to the report is very far away, okay. So I'm going to use this diagram to show you to what extent the phenomena due to arriving gravitational wave could be detected. So if we assume that this the binary black hole is located at the center of the circle, and each circle represents a different wavefront of gravitational wave at a different distance. From basic physics, we know that the intensity of the wave, any wave, gravitational wave, electromagnetic wave or radiation, sound wave, must obey this simple relation, namely the intensity of wave, which is proportional to the square of amplitude, were equal to the power of the source divided by the area of the sphere, the 4 pi r squared. So that is inversely proportional to the distance square. So as a result, the intensity will decrease very quickly according to the inverse distance square law. So that's why, let's just calculate the strength of magnetic field. Okay. According to their report, the mass of black hole is is less than 40 times of the mass of the sun. So I took these numbers and to work out the mass of black hole. Okay, for the binary, just double it. Not that much difference. And the distance from Earth can be calculated. That is in light year, which is 10 to the power of 9. If you convert that into meters, that will be the distance from the two binary black hole when merging occur to our planet. Huge distance. Gravitational constant, you can pick up from any textbook. And this calculated the gravitational field strength of this gravitational wave originate from the black hole, presumably. You can see that the gravitational strength associated with this gravitational wave is so weak. 10 to the power -45. compare with the gravitational strength of the Earth near the surface of Earth is 9.8. Can you see that? That is the quantitative figures. So therefore, you can argue that the force acting on any object, including Earth, due to the gravitational wave, is so weak. Is so weak. Okay. And this just actually to go to more detail. To what extent? This is the question. To what extent we can actually detect the arriving of this gravitational wave? So here is another estimate. Here I estimated the change, the maximum change in length of these two arms. Remember, these two arms is made by steel tube, and therefore, any other solid material, which was Yong modular would be slightly different, not big deal. So if I just assume this two tube is made by steel, and the length, the crossing area, just estimate. And this is Yong, this is Yong modulus. And she put, and this is how to calculate the force, the maximum force on this tube. Well, I use the mass of the tube, multiply the gravitational stress of this gravitational wave. And we can, so the mass can be worked out by using the product of the density of steel and the volume of this tube. So if you substitute these two numbers together, you will see that the force acting on the maximum force is just this small number, 10 to the power negative 36 Newton. Then we can use our engineering knowledge that people doing material science must very familiar with this formula. Namely, that the Young's modulus is equal to the ratio of stress to the strain. So if you base on this formula, we can easily calculate the maximum increase in the length. The number is that small, 10 to negative 33 meters. So what does it mean? When such gravitational wave arrive, the maximum displacement, maximum change in the length will be that small. Then how can we, we're going to convert this length into in relation to wavelength. For the laser, this group used is infrared laser. So therefore, I use this number, the micrometers are their average wavelength. From here, you can see the ratio of these two lengths is huge. Or in other words, the change in the length of the arm is so small compared with wavelength, right? So let's go to some high school physics. When we start interference phenomena, we know that if the two waves whose wavelengths, whose path length is changed by half wavelength, we would notice some change from this resultant doubled wavefront to this minimum called the destructive interference. So from this constructive interference to the destructive interference, you have to change the travel path distance by half wavelength. However, how much the change we can expect it when the gravitational wave arrived on the Earth? That much. So how could anyone use any state-of-art equipment to detect such change in the phase of the reflected beam, two reflected beam? Okay, that is a serious question. You can consider that. We can discuss further. But another issue I have to mention is that even when you go to the Einstein's general relativity itself, And you have you have bear in mind that there are certain abstractions you have to overcome before you use this field equation to do your modeling. First, in Einstein's field theory, in his general relativity, the curvature, the curving space-time is proportional to the matter and energy, as well as the stress. Very strangely, in Einstein's the tensor, this tensor TUV, not only represents the energy and the momentum, which correspond to the energy flow, but also there are 6 elements which represent this called stress. In the same way as we studied the material science, you will see that shearing force and the stress force. Okay, of course, this is analog, of course, but bear in mind that there is, no matter what you look at Einstein's field equation, there must be some natural or observable limit or a limit for this curvature. So basically, lambda is also another artificial parameter Einstein used, which just gives that empirical description of to make this curvature more realistic to the observation based on Newton's gravitational law. So in this field equation, to show in short, that the curvature, the change, the range of curvature change must be confined by the observation of gravitational interaction. You agree? So therefore, one cannot arbitrarily use different various large curvature to make their adjustment, to make their prediction. Why do I mention this point? Because if you go further, people would believe that this observation not only confirm that the gravitational wave, but also, more importantly, they also confirm the existence of the black hole or neutron stars. Okay. So this is another issue I would like you to think over again, because talking about the formation, so this is an issue of very fundamental. The formation of black hole, and as well as the neutron stars, was based on the argument that the field strength or curvature in terms of general relativity will increase enormously, so that the field strength, corresponding field strength, can be considered as huge, right? Actually, this particular point is called in mathematics is actually called the singularity. Singularity, this is actually the you know that this is simply the equation of 1 over r squared. When r approach to 0, so the value could be any number between around near the toward the infinity. Okay. However, what modern physics tell us is that there are 3 or 4 basic interaction. Relatively speaking, gravitational interaction is the weakest. And after that is the electromagnetic interaction, and then a strong interaction. So from this simple diagram, you can see that we cannot expect that the singularity, so-called, if you in relation to physical interaction, can be go as large as possible arbitrarily. They must have some limit. For example, for the gravity, the curvature is even smaller. Or the reason I mentioned the curvature for 3 interaction here is that to some degree, we still can use curvature to describe, say, the Coulomb force, right? So we still is the same. It's mathematically, it's all inversely proportional distance square. So my point is that in physics, in mathematics, the singularity can go as deep as possible if you wish. Okay, hence the curvature can increase to infinity. So that is what the singularity means. However, in physics, such maximum value must be limited by the actual interaction, right? So therefore, I believe that it is wrong to believe that the gravitational force can go as big as one wish, okay, in order to form the black hole and the neutron star. Talking about the neutron star, this is how the formation, oh, by the way, another issue is basic, is that the gravitational force would be the maximum on the surface of the body. Here I just use the Earth, but this gravitational phenomena is true for any body, for any huge body, including the remote, the huge star, which could be 10 times or even more, 100 times larger than the sun. But the fact is that once you enter to this, the body, the gravitational force will decrease linearly. At the center, for example, if you build a tunnel, and this object is like this white dot, the force between this object and the Earth will be proportional to the distance, rather than inversely proportional to the distance. That is a consequence of Gaussian's law. Okay, if you use Gaussian law, in other words, when you calculate the gravitational force, when the object enter into that object, the mass you can consider is just this smaller mass. Can you see this circle, origin circle? So the mass when you're trying to work out the field strength is reduced. So there's no point, there's no reason, there's to make the judgment that the mass, the density of a star can be increased arbitrarily large due to gravitational force. All right, so therefore, perhaps we also have to mention some background of what is a neutron star. So what is a neutron star? Of course, many people you have heard of neutron star, but here is just a recap. So this is ordinary atom. So you see, everything is made by atom. Every star is made by atom. Under ordinary condition like the Earth, the size of atom were determined by the size of the distribution of electron, while the size of the nucleus is very small. Actually, this scale is not right. Actually, the size of nucleus is much smaller than the size of the distribution of electron in space. So in 1932, and two people, and Badet and Zwick imagined that there might be, the strength, some magical force that can squeeze the object, such that electron would be forced to enter to the area of nucleus. As a result, everything will become neutral. So that is this squeezing force, magical squeezing force, could make this ordinary atom become a compact nucleus, completely made by neutron. So imagine that if each atom has become a neutron, then the density would increase enormously, right? Yes, this cartoon is interesting. This is squeak, probably just means squeeze. How could this happen? It didn't play. the only source of this squeezing process is gravity. As I just mentioned before, how could gravity play such a strange role to make this happen? So that is another related issue, but we can discuss more. That is the origin of the neutron star. Of course, also is the origin of black hole. And I think I'm going to stop here now. And because definitely I have raised many issues from the different perspective. Of course, I didn't claim that everything they published are fake, but certainly care must be taken in this context. I hope that this video will give you some different point of view on the observation of gravitational wave. And hopefully we will continue our discussing in much more in depth to explain that related issues. Please make your comment, and if you do like this video, please like. Okay. Thank you. See you next time. Goodbye.